So today's probably the most complicated lecture of the year to this point. I'm going to talk about building functions from applications and writing mathematical models. In other words, writing equations from word problems. So let's jump right in. In this first equation, it's described by we have a rectangle inscribed within a semicircle, and the equation of that semicircle is given by y equals 16 minus x squared. In other words, that y value describes the height of the rectangle. The base is described by the distance across, and you'll notice it's symmetric about the y-axis. We've got actually three questions asked in this problem. One, they want us to find the perimeter of the rectangle with the base of 2 units long. So let's just do that real quick and draw that. If I have a base of 2, that means it's 1 on either side, like so. So what I'm really doing is finding the perimeter of that yellow rectangle. In order to do that, I know my perimeter is given by the equation 2 length plus 2 width, or 2 base times 2 height. It really doesn't matter. Right? I'm going to call my length, why don't I call my length the horizontal? So in this case, I know my horizontal is 2 times 2, and my width is described as 2 times the height. But the height we just said was described by 2 times the root of 16 minus x squared. And in this case, that height is given by the y value at x equals 1. So that's 2 times 2 plus 2 roots of 16 minus 1 squared, or 15. In other words, 4 plus 2 roots of 15. There's your exact value. If I want an approximated value, I could go to my calculator, plug in 4 plus 2 roots of 15, and get an approximated value of 11 point, what was that again? 11.74. 5 when we round. Right? Now that's the first part of the problem. The second thing they want me to do is write an equation for the perimeter and the area of the rectangle in terms of x. Now, here's an equation for the perimeter. We know the area of a rectangle is length times width, but neither one of these two equations are in terms of just x. This has an x in it, as I've added to the problem, but it's not solely in terms of x because I plugged in the 2. If I want to write the perimeter in terms of just x, then what I have to do is say 2 times the length, but I know my length is the total distance across, and that's actually 2x values. My height, as we've said before, is the distance to that semicircle, which is the y value. All right? So I need 2 times my y values, and my y's, we said, are 16 minus x squared. So what I really have for the perimeter is 4x plus 2 roots of 16 minus x squared. That's an equation for the perimeter in terms of just x. Now, if I want the area is the length, and we just described the length as 2x, times the width. And we described that as being my height, which is root 16 minus x squared. So there's an equation for both the perimeter and the area in terms of only x. The last thing we want to do is find the value of the maximum area of the rectangle. Now, what's that actually mean? It means that for this equation of 2x times the quantity of 16 minus x squared, I need to find its biggest possible value. Well, we really don't have a way to figure that out because we don't have a number we can put in for a. I guess we could take and start just plugging numbers in and see what we get out. However, those numbers aren't necessarily guaranteed to be integers. So it could be any decimal number. The way we're going to take and do this is graph the function. And the function we're going to graph is this function 2x times 16 minus x squared. So let's get that calculator out. Move it over here. And we're going to go to y equals. We're going to graph 2x times square root of 16 minus x squared. And I'm going to double parentheses that. Now, I've got to think, well, what are some good values for x? Could I plug in 100? Definitely not, because this would then be 16 minus 100 squared, which we don't want to deal with. The biggest number I can actually plug in is 4, because after that, my square root goes to a negative. So what I'm going to do is I'm going to set my calculator up to see appropriate values of the curve. I don't want to use negative numbers because it doesn't make sense to have a negative x value. We're just going to use positive x values. So if I want to see this whole curve, I'm going to graph this in a window from 0 to, let's say, 6. That way I guarantee I'll see everything. And then my y values, if I'm talking about an area, I don't want to see negative areas. It doesn't even make sense. So I'm going to go from 0. Let's just pick a number. For instance, let's pick the number 2. If I plug a number 2 in for x, then that's 4. And the square root of 12, which is less than 4, so maybe 16. So I'm going to go all the way up to, let's say, 30. That way I guarantee that I'll at least see a good beginning shape of this graph. So we go ahead and graph that now. And you'll notice here's the whole curve from 0 to 6, cutting off at 4, because we said that's the high point of my x values. And this height actually describes my area, because I plug in an x and I get out an a, or an area. So I'm going to find the maximum value of that now. And we found maximums before by going second, calculate maximum, which is the number 4. It says go to the left of that high point, which is somewhere over here. Hit enter. Go to the right of the high point. I'm going to hit enter again. And then hit enter the third time. And what I have now is I have a maximum value of 16. And that would be in square units. And that maximum value occurs when I have an x value of, let's go back to the graph again, 2.83, let's round it. Okay? So we actually answered 4 questions within that one problem. Again, this is pretty complex. You're going to have to read carefully, have a little bit of geometric knowledge in your belt, and pull that out and use it. So here's the next problem. We've got a 1,200-foot roll of fence and a large field. It's going to be rectangular in this case, and you want to make 2 paddocks. What a paddock is 2 basically cells, holding cells, by splitting this rectangular enclosure in half. And we want to know the dimensions of the largest enclosure. So we want to know the length and the width. All right. If we have 1,200 feet of fence, that means all the solid features of this rectangle are fenced. So we want to say that 1,200 equals every single piece, or 2 L's. And in this case, I have 3 W's. The dimensions of the largest enclosure, what they're talking about, largest enclosure, we're talking about area. So the area, once again, is going to be equal to the length times the width, because it's just a rectangle, and that's the inside portion. Now, we're probably going to want to put this in terms of an x variable. It's up to you to determine what you'd like to call x. All right. If I was to take, in this case, and call my w the x value, then what I would have is I would have 1200 equals 2L plus 3x. And what we could do is we could now take and find a value for L in terms of x. So L is equal to 1200 minus 3x over 2. And if I wanted to simplify that a little bit more, 1200 divided by 2 is 600. And 3 divided by 2 is 1.5. X is equal to L. We want to take and maximize area. That's equal to my length times my width. And using the idea of the last problem, we want to put this all in terms of one variable. So my length is 600 minus 1.5x. My width, we said, was x. And now I can find my max area by going and graphing that. So you'll notice what I've done is in y equals, I've plugged in the equation for my area, and I have 600 minus 1.5x times x is equal to my area. What I next want to do is graph this in an appropriate window. Now I'm thinking to myself, well, I want positive values for width and length. Since this has a subtraction in it, eventually that's going to go to a negative. And I'm thinking, well, if this were 400, 1.5 times 400 is 600. So the highest I can go is 400. So what I'm going to do is I'm going to set my window up to go from 0 to 400, because that would get me a 0 length, if you will. Okay? My width would be x. Now, my output, once again, is going to be area. And area is going to grow rather quickly when I start getting big numbers. This is going to be somewhere around, let's just even say that this is 100. Then in this case, I'd have quite a large number, 600 minus quite a large number times 100. So I'd have something relatively over 10,000. What I'm going to do is I'm going to go from y equals 0, because I know I won't have negative areas, to about 20,000 and graph that. And you can see when I graph that, I have a shape which I can't see the height of. So my maximum area is going to be the peak height of this curve. I need to see a lot more. So I'm going to go back to my window, and instead of 20,000, I'm going to go 60,000, just as a guess. And a lot of this is guesswork. There's no right and wrong to your guessing in here. And then I'll go ahead and graph that, and I'll notice, hey, there's my peak. So now I have the whole function in my calculator. If I find the high point, I've found the maximum area. So I go calculate the maximum. We're going to go to the left of the high point. Let's find that cursor. There it is. Hit enter. To the right of that high point, bigger function, so it'll take a little more time to get over there. Hit enter and enter a third time. And we end up with a large maximum area of 60,000. That's our y value once again. And then if we want to find out the x value associated with that when your x value is equal to 200. Now, the question asks, what are the dimensions of the largest enclosure? I've just given you the x dimension. They didn't really ask for the maximum area. They asked for the x and y values, or the length and width values. I've given you the x. We can find the y by plugging back in. So if I want the length, that's just equal to 600 minus 1.5 times 200, which ends up being 300. So I have an x, or a width value, of 200 and a length of 300. And I've answered the question. Again, you can see these problems are a lot more difficult. In the next question, we've got an open rectangular box with a square base, and it's to be made of 48 square feet of material. So basically what I need to do is draw a picture of this. My drawing's not great, but here we go. I'm going to draw a box. Let's go this way. Let's say I have the front. I know my base is square, so something like this. And it says it's open, there's no top on it. Since I know the base is square, I can call the dimensions x by x. I don't know my height. And I have two things of importance in this problem. This 48 square feet, and we want to know the volume if I have a base with area of 4 square feet. So, if I have a base with an area of 4 square feet, the area of the base is just the area of this square. So I have 4 is equal to length times width, or x squared. In other words, my x value is equal to 2. If I know my x value is 2 and I want to find a volume, well, I now have to write an equation for volume. The volume of the box is x squared times h. Problem is, this isn't in one variable, and I'm going to need to get that in one variable. So the concept of this box is to be made of 48 square feet of material has to have something to do with the problem. And indeed it does. It's surface area. So the surface area is described as all the faces areas added up. I have a base area of x squared, and each surface happens to have an area of xh. And there's 4 of them, since I don't have a top. So my surface area is described as x squared plus 4xh, and I know also that my surface area is 48. So if I wanted to write a volume equation in terms of one variable, I can do that. All I have to do is solve for h. So I have 48 minus x squared equals 4xh, and if I want h by itself, h equals 48 minus x squared over 4x. Therefore, my volume is 48, or let's just go x squared since that's first, times 48 minus x squared over 4x. And now if I want the volume of the box that has a base area of 4, that means x equals to 2. So the volume is equal to 2 squared times 48 minus 2 squared over 4 times 2. In other words, I've got 4 times 48 minus 4 over 8. Or in this case, the 4 and the 8 is going to reduce to a 2, and 48 minus 4 is 44 over 2, or 22. What is this? It's in cubic feet. Cubic feet. Now, they want to know what are the dimensions of the box that result in the largest possible volume. I have to maximize the volume equation. So again, this turns into a calculator graphing problem. So let's go back to our calculator and plug in the volume equation in terms of x. So what I've done is I've graphed the equation of the volume in terms of x. Here's my x squared. I'm going to multiply that by, and notice I have a fraction, so my whole numerator is in parentheses, divided by my whole denominator, which is in parentheses, and I've double parentheses that whole set of fraction. Now what I need to do is I need to set up my window so I can see the graph. One of the things I pay careful attention to is the subtractions, because that's going to limit my domain. I don't want negative values for either the height or the width. Well, the width is never going to give me a negative value, but the height I get by the 48 minus x squared term, which means if I let x equal to 7, I'll have 48 minus 49, which would be negative 1, and that won't make any sense. So for my window, what I want to do is I'm just going to go from 0 to 10. That way I ensure that my domain is within that restricted set of values. And for my actual volume, I'm just going to pick a random number. Let's just pick the number 1. If I use number 1 for x, and we come over to this volume equation to the right, then I have 1 times 48 minus 1, or 47, over 4. So that's about 1 times, close to 12-ish. All right, and I know I at least need to look up to 12. If I pick bigger numbers, this is probably going to increase in volume. So what I'm going to do is I'm going to go from 0 to 100, since I know volume tends to increase pretty dramatically, and take and graph this. And you'll notice I see the entire function with a maximum value. And that maximum is going to be the volume. So if I take and calculate that, where I find a maximum, go to the left of the high point, and to the right of the high point, and calculate, I notice I have almost even numbers. Pretty close to 4. I'm going to call it 4 for our argument's sake. So I have a max volume I believe that was 48 cubic feet. Yep. When x equals 4, if I want my height, I'd have to plug 4 into this equation here. So if I plug 4 into this equation, I have 48 minus 4 times 4 is 16 over 16. 48 minus 16 is 32 over 16. And the height would then equal 2. Alright, so this next problem is going to shake it up a little bit. We've got a situation where solving the problem is going to be geometric in nature, but it's not going to involve a geometric figure per se. I have a situation where I have two cars, A and B, and they're actually 30 miles apart, B being directly east of A. And at a moment in time, car B is going to be moving to the west, and car A is going to be moving north. And the two relative speeds are going to be 90 miles an hour and 60 miles per hour. And what I want to know is at some point in time, as soon as they start moving, they're no longer going to be 30 feet apart. They're going to close distance on each other. And I want to know what is the minimum distance apart at some given period of time. And you'll notice what I've just created. I've created a right triangle. And I know that I have some a squared plus b squared equals c squared relationship or Pythagorean relationship that describes a distance. All I really need to know is to find out how far it is from here to here and how far it is from here to here. Well, if I want to calculate a distance and I have a miles per hour, I know that I have a physical formula that says distance equals the rate times the time. And if I say, okay, ready, set, go, and start looking at my stopwatch and watch time go by, I'm going to let time be my variable, because the more time that goes by, the closer distance I'm going to travel. My rate has been given in both cases, 90 and 60. So if my time is x, then this vertical distance will be 60 times x. My horizontal distance is a little bit different, because as I move this way, I'm closing the gap from 30. So I'm going to be moving at 90x distance, but I'm going to be taking that 90x distance away from 30 because I'm getting closer and closer. So what I really have is 30 minus 90x in distance here. My total distance, let's call this dt, my total distance apart is going to be given by that Pythagorean relationship, or the square root of 60x, that's the vertical distance squared, plus the horizontal distance, 30, minus 90x, quantity squared, and that will give me the distance apart. What I've done is I've modeled an equation to describe the total distance between the two cars. And what I want to know is at what time does that occur? Well, this again is a graphing problem, and we're going to pop that into our calculator and go ahead and graph it. So once again, I've taken and plugged my equation into my graphing calculator under y equals. Here's my square root. Now I have a whole bunch of stuff going on inside this radical, so I'm going to throw a double set of parentheses in and take my first term squared minus my second term squared, and then close all that off and to show that I've square rooted the whole thing. Graphing this is not necessarily tricky, but you've got to think about what are the key terms in this equation. We don't want to see necessarily negative values for distance. So you'll notice I have this 30 minus 90x piece in the graph. If I use x, which is time, as 1, and I'm talking about hours, then 1 hour is going to provide a negative value. So I'm going to go actually look at x values in my window from 0 to a half an hour and see when in time will that distance be a minimum. And then I'll throw in my y value from 0 to 100 because we don't want negative values either. Hit and graph, and you'll notice I get a curve that shows me some relative minimum value. I want to find that minimum, so I take and ask my calculator to go ahead and find the minimum. I'm looking at the left of that value first, hitting enter, and then the right of that value. Hitting enter again, And when we get our answer in this case, we get an x and y value. My x is in terms of hours. So what I have is I have roughly 0.23 hours gives me a minimum distance of whatever my y value was. So in this case, my minimum distance is 16.64 miles. Today was a tough day. Take a look at the problems assigned on my math lab. Let me know what you're solid with and not solid with in the lesson summary, and we'll do some brush up tomorrow as well. Take care.